I hope you have ever felt that just like fragrance of a beautiful flower, the influence of good character also extends till infinity. Just like gravitation field. Gravitation field also extends to infinity, and good character also influence people till infinity. Actually, what is infinity? So, infinity is actually a relative concept. If you know, when we say that for this pen, actually a 1 kilometer of distance is also a very big distance, right? But for me, 1 kilometer is not that much big. For Earth, it is just a small number, and for universe, just a point, right? So, for being able to escape from field of from gravitational field or electrostatic field or any type of field of a particular object, you have to go to infinity. Means in relative to dimension of that object, you have to travel a very large distance, right? For this point, this much length is infinity, but for me it is just a finite number, right? So actually today we are going to calculate potential due to a spherical shell using this concept. So what is actually a spherical shell? You have seen eggs, right? Chicken eggs. So those eggs have a shell, outside shell to protect the egg. So when we break the egg, take out those egg white and yolk out of that shell, we are left with the egg shell. Those eggshell are really very thin. It looks like all the mass is actually spread around a surface, not in a volume. Although there is also a thickness, the third dimension means it is a 3D thing and have a volume, but it appears to be like the mass is actually spreaded upon the surface. So we are going to use this concept. Means we are going to use surface mass per unit surface area, sigma, or surface mass density, instead of using rho, that is volume per uh, amount of volume per amount of mass per unit volume mass density is rho, but we are going to use sigma because here we are considering the shell to be just a surface, although it has a small thickness, very small thickness, dx, we can say that dx amount of thickness. So now we are going to use these two concepts and derive the equation to calculate potential due to a spherical shell, gravitational potential due to the spherical shell outside the shell, inside the shell, and on the surface of the shell. Actually, let me draw a spherical shell. This is a sphere, right? We can say that. Suppose although this looks something like a circle, but consider it to be a 3D object, a sphere, just like football. So we have to slice it. You might have seen any spherical fruit or a vegetable. Obviously you eat vegetables and fruit, you might have seen, and we just slice it. We slice tomatoes, we slice cucumbers and get a slice out of it. Suppose the cucumber was hollow, just like a spherical shell or a hollow cucumber, we'll get a ring out of it. Actually, when we slice any spherical thing, suppose a apple or a tomato, we get something like this seed inside, or watermelon also. We get a slice of some thickness. right? But if suppose this thing was empty inside, then we will be left with a ring, and if the thickness of this ring is really very small, we will get something like this, a slice, just like suppose we are slicing this sphere, then and I will take this out. If it is hollow from inside, then we will get something look like this, a ring, right? I don't have any example now to show you, just a physical example, but just imagine it that suppose I made a slice of cucumber, took it out, it was hollow inside, we are left with a ring, just a thin sheet of its peel, right? A thin ring of its peel. So this is the thing actually of a spherical shell. So suppose I am taking its center to be at point O and considering a point along a diameter AB, that is P, outside the shell. So if I draw the distance, let us suppose the distance is actually x, and from center the distance of point P is smaller. Actually we are going to take all the small rings, like say this one, this one, this one, this one, and integrate for potential due to all of these rings, right? I guess you are able to understand that. I'm just going to cut all the slices of this spherical shell, take all the slices, calculate potential due to each of the each of the ring, and then integrate it to get the total amount of potential due to this sphere. So suppose an elementary ring is at a distance x. Actually all the points on the ring is at a distance x from the point P, and the point P is at a distance smaller from the center. Suppose the sphere is of radius capital R. I am here the two slices. We will take two planes with what we cut the tomatoes or whatever our vegetable. We use a knife. Actually the knife is a surface. You might have seen that knife is a plain surface, just slicing it. If simultaneously I put two knives here, suppose CD and EF be the surface of those knives, then this will look something like this, and I have now a small ring, an elemental ring, whose thickness is considered to be negligible in comparison to its dimension. So now here let us suppose I am making OC and OE. Here you can obviously see that this angle is really very small. Although I have exaggerated the view that I have taken a very thick slice, but in reality we take a very thin slice, just like this one, to integrate. I have made this exaggerated view to show you the calculation. Suppose this thing makes an angle theta with the diameter AB. Now we want to calculate potential due to this ring. One thing we can see from this is capital R vector, this is x vector, this is small r vector. Here now we can see that capital R and x is along the same direction and r is in the opposite direction. So according to vector law of addition. If we square both the sides, we will get x square equals to r square plus capital R square minus 2 small r into capital R cos theta, right? The angle between capital R and small r, here we can see that this is theta. So let us differentiate it. So we will get 2x dx equals to, both of these terms, capital R is constant, the radius of the sphere, and the distance from the center of the sphere, small r, is also constant. So differentiation of constant will be equals to 0, and here the theta will be changing because for this elemental ring it is theta, but if I take a ring at this position, the theta will increase, and if I take a ring at this position, the theta will be greater than 90 degree, and for this position if I take a small ring, it will be nearly equals to 0. So we can say that theta is changing from 0 to 180 degree. So as theta is varying, we can differentiate it, and differentiation of cos theta is sin theta. So now we have the equation. We have to just now integrate the potential due to each cell, each ring. So from this we can see that the potential, we know the formula of potential, right? Due to a point mass, we know the formula minus gm by r. I hope you know this. If you don't know this, let me explain it for 1 to 2 minutes in a very fast manner. So if I am taking a, if suppose this is a point mass, capital M is here, the amount of work done per unit mass required to take a mass from infinity distance to a particular orientation, suppose at a distance capital R from the capital M mass, is the potential. Let me repeat it once again. The amount of work done per unit mass required to move a mass from infinite distance to a particular orientation at a suppose at a distance r from capital mass capital M. This position may vary. So suppose this is the condition. So suppose this mass is dm, this is the test mass. We are considering this mass to be really very small, dm. We are taking it from infinite distance to this position. So suppose at a particular instant, this is at a distance x from the mass capital M. So for this, from this point I am displacing it dx amount and trying to calculate the small amount of work done required to displace it in dx amount of displacement. So this will be equal to force into displacement, that is force is equal to g m m y r square, that is here x square into the displacement, we are displacing it a distance of dx, right? So we want to calculate the total work done required to move it from infinite distance to particular distance where it is at a distance of capital R from mass M. So the distance will be infinite to capital R, and here the dx is changing from the work done initially we are doing no work, so it is work done is 0, and finally we have done w work done to move it from infinite distance to capital R from the point mass M. So integrating this, we will get the value work done will be equals to g m dm by x minus with a negative sign, and dividing the total work done by mass, we will get the amount of work done per unit mass, which will be equals to minus g m by x, which is known as if we integrate this, we will get r here. R, or this r may vary, you can put here small r, capital R, or any constant value. So using this we can calculate that the potential at a point due to a point mass at a particular point at a distance r from the point mass m will be equals to minus gm by r. I hope everything is clear. So now let's come to the topic to calculate the potential due to this spherical shell at a point P. So now we are going to integrate. We have the value G because it is a universal gravitational constant, means it doesn't depend upon any medium, anything. It depends upon one thing, that the medium is in the universe. So G, we know the value of G. We want to know the value of this ring, right? Suppose the mass of this ring is dm. Dm will be equals to the surface mass density into the surface area. So the surface area will be equals to here this thing. The suppose I had the ring of the peel of cucumber, right? If I cut the ring and just open it, I will get a strip. Here the breadth of the ring will be this much, that is L equals to r d theta. So this will be equal to r d theta, and here this length will be, as I have opened the peel of the ring made of the peel of the cucumber. As I open it, I will get the perimeter as the length of the ring. So this will be equal to 2 pi r dash. Suppose the radius of this ring is r dash. So from this triangle actually you can see the value of r dash. R dash will be, as here this is r making an angle theta, you can say that r dash will be equals to r sin theta, because sin theta equals to perpendicular by hypotenuse, and from this perpendicular will be equals to sin theta into hypotenuse, and we can say that r dash equals to, this will be equal to 2 pi r sin theta. And now the surface is equal to 2 pi r sin theta into r d theta equals to 2 pi r square sin theta d theta into the surface mass density, which is equal to mass by total surface area of this spherical cell. What will be the surface area of this spherical cell? As the radius of the spherical cell is capital R, so you can say that the surface area of the spherical cell will be equals to pi r square. So putting all the values, assembling into the equation, we can say that mass by 4 to the volume 2 pi r square sin theta d theta gm by r. R is here the distance, capital R and small r, right? I hope everything is right. Gm sigma into surface divided by distance. Oh sorry, actually here the distance, we can see that the distance is x for each point on the ring. For P, the each point of ring is at a distance x from the point P. Let me show you something. I hope this can help. Suppose this is the ring. I have taken this slice out. Now I have this ring, and here the point is P. The point is now here P. From this you can see that all the point on the ring is at a particular distance, is at a constant distance from this at this end. So let me show you. this is the distance of this point from ring, right? This is x, right? This is actually the along the diameter AB. This is the radius of the ring. I hope everything is clear. Now I am working on the whiteboard. See this. So here the distance is x. Now we want to calculate the total potential. Here it is the small amount of potential. We have to integrate it from 0 to V, right, to get the total potential. And here we are integrating actually from this point to this point. We are taking small elemental rings from this point to this point. So here I have the d theta to integrate with, but I want a term in dx so that it will be easier for me. So I want to just use this equation. Here I can say that x equals to 2 will be cancelled out. X will be equals to small r into capital R sin theta d theta by dx. So here I can put the value of x, which will be equals to minus gm by 4 pi r square into 2 pi r square sin theta d theta by this value small r capital R sin theta d theta by dx, which will be multiplied in the numerator dx. D theta will cancel out, sin theta will cancel out, 2 pi r square will be left with a 2, and here now we have equals to minus gm by 2 smaller capital R dx, right. So now we are integrating dx with respect to dx. So what is the distance is changing. Suppose I have taken a really very small ring. I have sliced the ring from this portion. So here the x will be nearly equals to this much distance, and if I take the final ring at this position, take a small slice of ring, the distance will be equal to this much. Here the distance is this is capital R, this is this is smaller, this is capital R. So this much distance will be equal to R plus R, and here this is capital R, this is smaller, this is capital R. So this much distance will be small r minus capital R, right. So we are integrating from small r minus capital R to small r plus capital R. So let me put the limits. Small r minus capital R to small r plus R, and here also small r minus small r plus R, small minus capital R to small r plus R. Everything I am doing is according to the book of mechanics written by D.S. Mathur. So you can refer the book. And now I am integrating this. Here everything is constant. You can take it out of the integration in the integral. So now we are left with integrating dx, and if I integrate dx, I will get x, and if I put the values r plus r minus r, then I will get capital equals to minus gm by 2r small r into capital R whole into 2 capital R, right. You can do it yourself and say that it will come out to be 2 capital R, and cancelling everything, I will get the total potential to be at P due to the whole sphere will be equal to minus gm by small r. Here we can see that I had derived the equation minus gm by x. Suppose the mass was m, constant was g, and x was the distance from the point mass. Suppose this sphere has its mass concentrated at the center O, then it looks like sorry, I told the actually answer. So let me once again repeat it. I told that for a point mass, this is the equation. Means if a point mass is at a position, to bring another mass from infinite distance to a point where it is at a distance x from point mass m, the work done per unit mass will be equal to this much, that is equal to potential at a point x, the potential due to point mass m at a distance x. And here we can see that here everything is minus g, mass of the sphere, and the distance is smaller. Just feels like the whole mass of the sphere is concentrated at the center, right? So here I have the equation B equals to minus g m by r. If I take the point to be on the surface, I can put the small r to be equal to capital R. So for a point on the surface, the potential due to this spherical shell will be equal to minus gm by capital R, right? And for a point inside, you can do actual, if you change the limit for the point on the surface, you will get the, if I take the initial ring here, the point is at a distance 0 from the ring, so the limit will be 0 to this point is at a distance of 2r, d equals to 2r, so 0 to 2r, and putting the value you will get that 0 to 2r, 2r will yes, and here actually the distance from the center is capital R, so you will get minus g m by 2 capital R into capital R into 0 to 2r, means you will get 2r minus 0 equals to 2r, and will get minus gm by 2r, gm by r for a point on the surface. Similarly, you can use the same integration to calculate the potential inside the spherical shell. So for a point, suppose, let me once again draw a sphere. Suppose this point, this is the point P at a distance small r from the center. So if I take the initial ring this here, the distance will be equals to capital R minus small r, and for this point this will be equals to capital R plus small r. So putting the again the limit x, capital R minus small r to capital R plus small r, this will be equals to 2 small r. And if I put here instead of 2 capital R, I put 2 small r, I will get the value minus gm by r. This means inside the sphere the potential is constant, right? So for a point inside the sphere and on the sphere, the potential is same and is equals to minus gm by capital R, that is the radius of the sphere. And for a point outside the sphere, it depends upon the distance from the center and is equal to minus gm by small r. You can get notes on these things. Actually, those are my notes I make for taking classes. So you can use these to once again revise these topics. Now we have idea about potential due to the spherical shell. It's time to study about field. We know that field vector is the gradient of potential, right? Like force is the gradient of potential energy, field is the gradient of potential. Actually potential and potential energy is different. Potential energy is stored in the body, and potential is the amount of work done per unit volume. Like you can say that suppose at infinite the potential is 0. We actually cannot calculate the potential energy, because if you know that in chemistry you will study that we actually do some reactions and all, and by just subtracting equation we can get the value of change in potential energy, not the exact potential energy stored in the molecule or the lattice, but can calculate the difference. Just like this we can calculate the difference, and here we are assuming that at an infinite distance the potential is equals to 0, and when we put the thing at a particular distance or in a particular manner at a distance of suppose x from the mass or from the charge, we will get the potential change of this much, right? Because the body have itself some potential energy, and when we bring it to a particular environment where there is some field, some potential some field, then it feels some change in potential. So we calculate that change in potential, and here I am going to put the value of potential and differentiate it, that is take the gradient actually. If you are now doing B.Sc, you know that curl divergence gradient. So gradient is a operator that is denoted with del or nabla. So actually we use this operator to change a scalar quantity to a vector quantity. So taking the negative gradient of potential, we will get its vector value, that is field. So here we know the value for inside, outside, and on the surface the value of potential. So we can use that value to calculate the field, the gravitational field. Inside it is minus gm by r, outside it is minus gm by small r, on the surface minus gm by capital R. Here I am starting with the situation outside. So this after differentiating means taking the gradient of this potential vector, I will get this as minus g. This is r to the power minus 1, which means taking the differentiation I will get gm by r square, right? Gm by r square. Here if I yes, a negative gradient means a negative sign will also be there, and here if I take the field due to the sphere, the spherical shell at on the surface, it will be equal to minus gm by, here if I put small r value equals to capital R, I will get minus gm by r square, but g, m and r is constant for the dr, so differentiating this will result into 0. We are differentiating the same thing here and on the surface and inside the surface, but getting different results. Why? Because for on the surface there is actually, let us suppose here we are on the surface. If I take a sphere containing the point, I'll see that some mass is inside this sphere. We'll talk about this theorem I guess in some other chapters. So if I take this sphere, there is some mass inside. Some mass is inside means there is some field, and as there is some field, it will be equal to minus gm by r square. But if I take a point here, there is no mass inside containing this sphere. So this here the potential is the field is equal to 0, because there is actually no mass inside it, and as there is no mass, nothing will influence its position, and we can say that if the here the point is this point will attract it with some what you say is force, and this point will also attract it, and the total vector sum will be equals to 0. So that's why no field acts on a point inside the spherical shell. That's why the field is 0. But for the surface, there is some mass attracting it, because suppose this is a sphere, a point is here, this mass is attracting it along this direction, this mass is also attracting in the same direction, and the net resultant will have some value, as some force is there, some field is there. And this is for today. So in the next lecture, here I have written field equals to negative gradient of potential. So these things also are seen in case of electrostatics. So in the upcoming lecture, I am just going to compare gravitational potential and field with electrostatic potential and field. For today, I have a homework for you to calculate the potential due to a spherical shell containing some charge q. And here this thing is really very easy for you. I have made my notes a little bit complex doing double integration. I will tell about that in a simple manner in the upcoming lecture. But for today, your work is to take the charge q on the spherical shell, use a sigma surface charge density, not mass density, and calculate the potential in the similar manner. There is no difference in the calculations, you can do it yourself. I will try to tell you about it in the next lecture, but still do it yourself. Thank you.